Skeleton proto-RNA selecting exactly 22 amino acids. We've got no time left now.
Good morning, everybody. Thank you very much for patience. This is done at the last minute and will be a bit rough and ready. But I have a preprint on this. The suggestion is that a proto-RNA arose in zeolite tubules through stacking of dimer pair RNAs that enabled consistent production of peptides and replication. And also that the first membranes were actually silicate shells rather than lipid or sugar based. For life to have naturally evolved on the Earth's surface meant that we had to have an abiotic mechanism for production of RNA. We needed shelter from UVC because of its destructive potential and an early viable cellular enclosure. I'm suggesting that RNA, as I said, RNA arose in zeolite tubules. They're about 10 angstrom. So you could stack dimer RNA base pairs in there and probably have room for the passage of amino acids. I suggest that between each pair of dimer pairs, you have a steric pocket that could have selected by amino acid side chains. The amino acids that could have accessed the tube would be relatively small and limited in number. And interestingly, when you start looking at the numbers, it could, and looks like it does actually select the 22 amino acids, and also when you take it a step further, explains the codon table. I started off fixated on dimer pairs because DNA is based on dimer pairs, but a couple of months ago it occurred to me, well, why not a dimer pair and a single base, dimer pair, single base, and that would reduce the steric specificity of the pockets. And because you're dealing with 3 RNA bases out of 4, actually totally replicates the codon table. The use of minerals as a cradle for life is not new, and people like Hazen and Smith have proposed this, and there are numerous papers suggesting it. So I'm just taking other people's lifetimes work a step further potentially and hopefully. So the important factor is that you've got specific and differing sets of RNA bases, which is going to create a different steric pocket, and that hopefully would or might be capable of selection of amino acids. So this is very, very simple drawing. There was an alternative I suggested. Now it gets more interesting because the distance in the RNA stack is about 3.4 angstroms, and the relevant length of an amino acid is 3.4, 3.5, depending on whose figures you look at. So it is actually dimensionally feasible, which is kind of, wow, that's kind of interesting. And so here we've got the pairs stacking. They're probably going to move on because of polarity and things to one side of the zeolite tubule. They may spiral as in RNA. They're going to, there's strong polar attraction to zeolite tubules, and that's shown with a number of organic molecules. So here we are again. It's a slightly abnormal configuration of a peptide chain, but in a solvent situation, it probably would sit flat and align within the tubule, the side chains sitting within the steric pockets, and the rest of it sort of nicely aligning down the tubes. So again, so you've got the 3.4 or 34 angstrom. So you've got these 2 dimensions that actually would work if the project was feasible. And if you, I started out looking at normal canonical forms, and that would give you 16 options. I then thought about non-canonical forms, the common ones, that would give you 32 options. The kind of uracil, cysteine connections, I mean, they do happen, but they're not very common, and I've excluded them, but there's ongoing thought in my mind on that. So if you then table the possible options, you get there's 12 there and there's another 4. And some of them are, so you've got where you've got AU, UA, UA, AU. Those are kind of reverse scenarios. So if the side chain was relatively symmetrical, it would probably flip to the correct place. So you would have the possibility of creating quickly. So we're going back one. We've got back 2. We've got 1 to 20 are functional. Then you've got non-functional reverse orientation, which could either be a stop pocket or a duplicate. And then you've got these ones where you'll get some sort of steric hindrance on stacking. And the uracil, I suggest, will be very rare. And the cysteine will probably occur, but not very often. So that leaves you with 20 clearly working, some rarer options, half of which will be duplicates, some which will not occur at all, and 4 of those will be non-functional stop pockets. So you've got what looks like the possibilities of 22 different amino acid selections. And as well as having, as I mentioned earlier, as well as having a dimer base steric pocket, you could have a dimer base single base steric pocket, and that effectively becomes the codon table, because you would have all of the options that you see in the codon table. And what I took the previous data and extended it and then linked it back and numbered it and referenced it back to the codon table. And as expected, it does produce all of the options in the codon table, which is kind of interesting. And logically, because you're selecting 3 bases out of 4, so where else is it going to go? And the second part of this is that for protection against UVC in light, a mechanism is needed. And one of the really interesting and important properties of silica is that it absorbs UVC but lets visible light through. So by creating either vesicles in silicate or initially sheets on stromatolites that would be kind of wibbly-wobbly, that would collect abiotic building blocks of life brought up in possibly a freshwater hydrothermal system. So you've got atmospherics, lightning, solar flares, eutectics within ice, buildup of ice, melting of ice, flow of ice into hydrothermal systems, and up through zeolites are produced in volcanic eruptions and things. So zeolites are within the frame, and they're coming up through zeolites and collecting under silicate sheets that could have a silica gel layer, which will provide interesting chemical in terms of kind of chromatography type effects and things. And it would be exposed to sunlight, so you'd have sunlight energy for sulfur-based reactions. Silicate will form pores. It's a better material in a sense than either lipids or sugars, because it's easily available. It will crystallize out as solutions cool. It forms quite sophisticated structures, just as silica. And once you start adding amino acids and proteins, you get much more sophisticated structures. It forms pores, lower sensitivity to pH. It's much more robust. It would be more stable in mineral polar waters. It encapsulates, and it would encapsulate lipid membranes and sugar-based membranes. So over time, as UVC was excluded by ozone and things, could leave or go independent of their silicate shells. That's kind of the nub of it. There is a preprint up on ResearchGate. I will put the latest version up, which deals with the 3 codon idea. There are a number of other ideas. It's taken me probably about 5 years to get here. It didn't happen overnight, and it couldn't have happened without all your research, providing the backbone and the basis for the idea. It is an idea. It is a hypothesis. I live in a dark corner. I have no access to lab. The opportunity is there. If people think it's interesting, to try and take it away and do something with it, and I'm delighted for that. And I was speaking to a gentleman last night, and he was saying this particular zeolite, has potassium, might be interesting. Absolutely brilliant. Thank you very much. I don't want credit for anything that I haven't sort of brought to the table, and I hope that's interesting. If you've got any thought-provoking, if you have any questions, please do ask, and I'll do my best to address them.
Thank you very much. There's a question online, but in the meantime, while I sort that out, Sohan.
Thank you very much, Bob. I think all the 22 amino acids wouldn't have been present.
No, absolutely.
Right.
No, absolutely. I mean, I deal with that in the quite long preprint. At a certain number, 18, possibly some say 11, some say 18 were present. Some may have been too long. So absolutely, yeah, totally agreed. I mean, but it's just interesting that in the longer term, it seems to be pointing towards selection of these 22, which is thought-provoking.
Yeah, thanks.
Okay, so there's oh gosh, just lost it. Sorry. A question here. Can you talk more about whether some zeolites are favored over others? Does the shape or size of the various zeolite minerals make a difference?
I wish I could. We have an eminent geologist here. Geology is not my field, and I think it requires a really specialist knowledge of these zeolites. You're looking for something that has an 8 to 10 angstrom tubule, although zeolites and other silicates can actually kind of conform or change shape where they're interacting with organic molecules. But I wish I could. I wish I had the resources and the capacity to direct people further as to where to begin to look.
Well, there's a follow-up question on that, which I think I know the answer to because you've already said it, but it starts out, do you have any plans to run an experiment or set of experiments? So I know the answer to that, but perhaps you can answer in general terms.
I wish I could.
Well, I know, but the specific question is, would you add some pH? I mean, I presume that means it lower the pH, or electricity, or other gradients, effective electric fields, protons.
I think pressure, mimicking what happens in a hydrothermal system. So those flows, you need desiccation, whether that's from sunlight or from geothermal energy to drive the condensation reactions of the amino acid. You need the flows to push the amino acid or the formed peptide to push the amino acid to deliver the amino acids to push the formed peptide chains out. The RNA bases are probably sufficiently polar that they're going to remain attached to the zeolite tubule. The amino acid could then leave the system, or it could go into another tubule attached to the zeolite tube, and the RNA could actually kind of arrange themselves around the amino acid and then attach to the zeolite tube, so providing a kind of a method for replication. You've got the capacity for stop codons, inverted commas, so you're only going to get relatively short chains, particularly if the number of amino acids is restricted. But interestingly, suggestions are that early life was possibly made up of repeat peptides and silicons, and things which are involved in creation of shells for diatoms and things are repeat peptide chains. And yes, I mean I just sit in a dark corner and do a lot of thinking and fund myself, which has advantages because you have no restrictions on where your thought processes go. But but it also has significant disadvantages in terms of what you can.
Well, there's
what you
nothing
can
wrong
do.
with theorizing.
And thank you, it's just serious. And but some of this, like sometimes you did previous work with small glass tubules under pressure where they saw all sorts of reactions going on. So these are areas which people may be able to find ways to look at and replicate. And it's people like Professor Hazen and Deemer and Damer and all of these people who have been thinking, they just haven't put this step in there.
I think there's a general point that doing these kind of reactions with some sort of solid support there has a lot of advantage. Ice as well. I mean, we heard a little bit about microscopic ice particles in space yesterday, but Philip Holliger, for example, he's this selected polymerase ribozyme that he's made becomes much more processive if you do it within the cavities of ice. And there's a lot of advantages to thinking about these things, I think. Well, we've got some more questions online, seems to. If we say that protocells have silica-based membranes, why did these membranes evolve into phospholipid membranes?
I think they lined because you're having a phospholipid membrane is kind of isolating you in terms of the biology that can go on within the cell. And as I would see it, you were forming maybe sheet blisters to start with, and then vesicles, and then the lipids came on the scene, and the lipids migrated to the outer maybe as a single layer, and then as a bilayer. You may also have got an intermediate sugar protein membrane. So that doesn't exclude. So as things change and move on, and UV diminishes, or they move to deep oceans, then they wouldn't need that silicate and may evolve to just being a sugar polymer or a lipid membrane over time. So it doesn't, the interesting, this doesn't exclude, it just provides a protected intermediate layer from UVC and from quite harsh marine or inland liquid conditions in terms of pH and mineral concentrations and physical interventions, meteorites and things that we've seen that would provide a possibly more robust intermediate towards going to liquid.
Well, I mean, I think anybody that's ever blown a soap bubble knows that amphipathic molecules very naturally form a bag-shaped assembly. And going back to what we were talking about yesterday with what the definition of life, clearly the only way you can get a local lowering of entropy is to encapsulate. And so the cell is the atom of biology.
And silicates have these amazing properties until you start like looking and reading and seeing how they will form really sophisticated structures easily without a lot of help. And people have used small silicate spheres or enclosures to mimic cells and cell membranes and pores, and they say that they are, the people who did this particular paper said they are a really good model and would make a good model for research into early life.
Right.